All right, so you only have to listen to me for 1 hour tonight. I know, it's great, isn't it? I hope the test wasn't too bad. If you, if you did the review packet, I think you should have done all right on it. If you studied the review packet, and considering it was the same questions on the review packet, it might have been a little bit long. Sorry. I don't think the final, at this point, I don't think the final will be comprehensive, because that would just make it too long. So we'll probably just be starting with chemistry and going forward from there. Tonight, we're going to do kind of 2 chapters pretty quickly, actually. Luckily, the first one is actually not that much stuff in it, really. It's kind of an overview of chemistry. Last week, we started chemistry, but really that was still physics, like I said. This week, we're really going to get into the actual chemistry, and I think we'll go from there. And really, I know some of you guys at the beginning of the year were like, oh my gosh, chemistry, I never liked chemistry. Well, I wasn't very good at chemistry when I was in school, and I didn't love it either, but I think the nice thing about the way we're going to study it here, we're not going to go too in-depth. It's going to be kind of like physics, where we're going to do a nice broad picture of chemistry, and I think you'll find it somewhat interesting. Chemistry is what they call the central science. Chemists like to say that because it's not physics, if you ask me. But they call it the central science because it draws from physics, it kind of gives you biology, and it kind of gives you a lot of earth science. Astronomy, I don't know, that's a tough one for me. I think astronomy is more physics than chemistry, but inside a star and inside planets and gaseous clouds and things like that, you can find a lot of chemistry. So when they say it's a central science, that's basically what they mean. Everything kind of comes in or goes out from chemistry. Chemistry is what? Study of matter, really, and the transformations that matter can undergo. Okay? We already said it was a central science. It's a materials science. It's the stuff in everything has to do with chemistry, like how stuff's put together in compounds and mixtures and all that kind of stuff we'll talk about tonight. Almost everything humans have created, right, rely on some sort of chemistry, whether it's a microchip or whether it's this metal chair here, has something to do with chemistry, right? Especially today. I mean, you can't go more than 1 foot without seeing something made of plastic, and that's all chemistry, okay? All right, so when we talk about chemistry, we have to talk about things that are submicroscopic. We kind of mentioned this the other night, where you can't necessarily see molecules with a microscope. They're just too small. There's 125 million trillion atoms in 1 grain of sand, right? That's a lot. I mean, when you think about how much that really is, when you talk about those kind of numbers, molecules and atoms are just so small that we can't see them with light. Okay, we're going to talk about physical properties and chemical properties. And physical properties are the look or feel of a substance. Okay, so if you look at gold over here, right? Well, gold's opaque, can't see through it, right? With light, it's yellowish. That's a physical property. When does it melt? What's the density? All these things are physical properties, right? Same thing with the other 2 things, diamonds here and water. Okay, a physical property is like how you describe something. Okay, and you can have physical changes, which is how when you change an object without changing kind of the substance in the object. Okay, if you break something in half, you've done a physical change, not a chemical change. Chemical change is when one substance turns into another, and it's going to use electricity in some form or another. Okay, electric atoms and so forth. Okay, Frank, all this is, remember, all this is online, so if you don't want to write it all down now, you can always find it.
Remember better when I write things down.
Oh, no kid, sorry. Maybe I'm going too fast. I do want to get through a lot of this stuff tonight. So a substance, on the other hand, is, you've got the atoms in it, right? But it's also how those atoms actually connect to each other, which is kind of the coolest part of chemistry, is all these, when you look at hydrogen, which is a flammable gas, and oxygen, which makes everything burn, and you combine the 2 together, and you end up with water, which puts out fire and that sort of thing. And that's a chemical change when hydrogen and oxygen come together, and that defines the substance. right? It's how those molecules come together. And at the end of this, we'll get to more, some more details about how some of this stuff happens and when they connect together. And in terms of water, for instance, because of the way water combine, like the oxygen and hydrogen combine, you get these cool things like the fact that that ice floats, and the fact that water is a natural solvent, or it's the best solvent, and all these kind of cool stuff. So anyway, I think chemistry is neat in that sense. All right, question. Physical or chemical change? Oxygen and, let's see, methane combine together to produce water and carbon dioxide. Physical or chemical?
Chemical.
Why chemical? Did things change? The substance change? Yeah. Yeah, you're not like, yes, you're breaking these up and all, but you actually get totally different molecules out of it. Okay, methane, you would not want to like try to swim in methane, right? And oxygen, you know, we breathe oxygen, right? But if you combine the two together, you get carbon dioxide, which we breathe out, and you get water, which we also breathe out, and that sort of thing. So it's definitely a chemical change. Okay. Again, how do you make the difference between chemical and physical change? Physical change, same material. Straight up. You haven't changed the material. Chemical change, new materials. Okay? You can change the physical appearance of something with a chemical change. I mean, if I took, or a physical change, if I took a glass ball and I smashed it up, right, it's probably not going to look the same. Still a physical change, though, because I haven't changed the actual glass. Okay, now if I melt the glass, well, even melting it really is a physical change. But if I melt it and then mix in some color or something, that might make a chemical change in that sense.
One thing that threw me off in the book is they say the act of growing. You know, a child growing into a man. You know,
Yeah, the act of growing.
It's not a physical change.
Oh, it's a chemical change. Yeah, the act of growing is a chemical change. Yeah.
That threw me off.
Well, yeah. I mean, think about it. Are you? Well, most of your cells do go through some sort of change, but yeah, I mean, you're a very different like chemical person. I mean, in some sense, a baby is chemically similar to an old person, right? But the chemicals themselves have done a lot of changing over time. Yeah. Okay, here's another question. Which is physical and which is a chemical change? Melt a piece of gold. Physical. You're not changing the gold. It's still gold. Tarnishing a piece of silver. Chemical, because yeah, when tarnishing is actually like changing the actual physical silver by having it react with air. Okay. All right. So yep, when you tarnish, well, actually, sorry, I lied. It's not really air. It's silver becomes silver sulfide. Right. Silver becomes silver sulfide. Okay. All right. Okay, we only started a few minutes ago. All right, so that's physical and chemical changes. Okay. When you look at elements, right, we know that elements are just the letters that you find on the periodic table, which is what we talked about last week, right? The little element formula or element like name. Okay. When you actually want to talk about compounds, which are connections of or atoms, okay, you have to come up with a little formula to do that. We'll talk about some of the rules here. There are a lot of rules. In fact, there's rules that chemists have made up to say any combination of molecules you can describe with these formulas. But the formula, like the way to do this is kind of intense, right? Some of the longest words we have in English are just formula names. They're like hundreds and hundreds and hundreds and hundreds of like letters long because they combine all these atoms together in their formula names. So it's, we're not going to learn all those, but we're going to talk about some of them, right? Like oxygen, you can have two oxygens together, two atoms of oxygen together. We just call it O2, right? You can also have three atoms of oxygen together. We call that O3. Also called ozone, actually. You guys might have heard of ozone before. If you ever done anything with electric motors or anything, there's a distinct smell that comes from an electric motor, which is actually ozone. And you've heard, of course, of the ozone layer, which tends to go away when you have too many chlorofluorocarbons in the atmosphere. Okay, So we have the formulas. We can also just, things that don't necessarily react, we can also just use their atomic formula like gold. Okay? All right. When we talk about compounds, we're talking about substances that have atoms of different elements. Okay? So if you just have O2, that's not a compound. It's still an elemental substance. Right? But if you have, so sodium and chlorine, right, when they're together, that's a compound. Okay? And we actually call that sodium chloride or just table salt. Yeah,
So
Tom.
like an alloy would be a compound?
Careful. Alloys, yeah, in general, alloys are compounds. You got to be a little careful with sometimes they're actually mixtures or solutions or whatever. But yes, in general, an alloy is a compound. Yeah, yeah. Okay. And here's the cool part: compounds generally have much different properties than what they're made of. So we kind of talked about this earlier. When you mix, well, this is a good example: sodium and chloride. Sodium is I forgot to download the video. I'll put it on, I'll link up online. Sodium is a metal that's like butter. It's very smooth, you can cut it with a knife. Not quite, it's maybe like cold butter. You can cut it with a knife. If you take some sodium and drop it in water, it'll explode, which is kind of cool, right? It explodes basically because it has a very fast, very hot reaction with the water, and it creates hydrogen, and that hydrogen gets so hot it explodes. So it's pretty cool.
I've seen videos.
Yeah, if you look up online, I'll link to a couple of videos, but if you look up online, sodium pond or sodium in a lake, there are people who take big chunks of it and like hurl it into a lake, and it just blows up and then blows up and blows up. It's pretty cool. Pretty cool stuff. But anyway, chlorine is a gas that they used as a chemical weapon in World War I to kill people, right? Sodium chloride, you put on your French fries, and you eat it all day, right? And it's tasty, and it doesn't kill you, right? But the two elements together, separately, would be bad if you tried to do stuff with those individually. Okay, when it's combined, totally different type of substance. Pretty cool.
Sodium chloride, man-made salt, and then natural sea salts, different compounds.
Natural sea salt has a lot of sodium chloride in it. It also has potassium. What is it? Potassium chloride, I guess, and lots of other minerals and so forth in it. Yeah, but sodium chloride is like just table salt, just itself by itself, table salt. Now, the table salt you actually put on your fries also has some iodine generally in it, which is good for your health. So they put that in there. So it's good. Okay, so we already talked about this table salt, and I was going to show you this, but I forgot to download those, so I'll have to link to them. But it is pretty cool. I guess I could also link to like World War I, like chemical poisoning videos, but I won't do that. Okay, when we talk about naming, there's these rules. We're only going to go through some guidelines. I'm not going to stress about them, but when I talk about something, you'll have to kind of go, oh yeah, that makes sense, because hopefully we'll get it right, but I don't always get it right either. There's some guidelines here. Guideline 1, you start with the element that's farthest left in the periodic table. Why? They just made it that way. Whatever, right? For the element to the right, you add IDE. Okay, so NaCl. Na is sodium, so you'd say sodium. Chlorine, you just do ide, so it's sodium chloride. That's the rule. Okay, and chemists love rules like this, by the way. They love it. They're all about rules and like putting stuff together. That was guideline 1. Leftmost, and then add ide.
What if they're in the same group?
If they're in the same group, it's a little tricky. Sometimes you can probably call it either or, but there's also probably other rules we're not going to worry about. And yeah, there are other rules that you can look up if you want. All these books on it. If you have 2 or more of a particular atom, you can say mono or di or tri or tetra, et cetera, et cetera, et cetera, for as many as you want. But we're not going to worry too much about all the details there either. Carbon monoxide is CO because it's got 1 oxygen. Carbon dioxide has 2 oxygens. Carbon dioxide, di being 2. Okay, so if you never knew all this stuff, kind of, hey, that's how carbon dioxide got its name. Yeah, I know. I mean,
instead of di, what do these bi for 2?
Let's see. Mono, I think di is maybe Greek, and bi is Latin, or maybe it's the other way around. I forget. Yeah, so they just picked one. Yeah, I picked them.
See, Why is it confusing? It could go both ways.
All right. Guideline number 3. If there's a common name, use it. That's kind of a silly guideline, but we use these names like we don't say it's H2O. We don't say H2O is dihydrogen monoxide. Like you could, right? Dihydrogen monoxide, but we say water instead. And that's actually an interesting one, dihydrogen monoxide. This kid, I guess 1 or 2 kids did a science fair project where they said the dangers of dihydrogen monoxide, right? And it was, and they had all these dangers like, can cause suffocation, can too much will, if you drink it, you can, drink too much and it's, bad for you, blah, 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 and this and that, and it, it can crush you and all this stuff. And they were just talking about water, so kind of funny. They won first prize too. And then H2O2, anybody know what this one is? Did you already read it? Hydrogen peroxide, yeah. Why per? I don't know. Oh yeah, you can see it on me. What's that? Used for cuts, yeah. Tends to kill things like bacteria. Okay. Legionnaire, yeah, maybe. What's the name of the compound? It's CBr4. It's not CBr4, right?
Carbon tetra.
Carbon tetra, meaning 4 bromide. Yep.
And what is carbon tetrabromide?
I don't know what carbon tetrabromide does. I don't know. Not sure. Not sure. Okay. So the next thing we're going to talk about is how do atoms and molecules actually attract? Now, I said before, it's one of the main forces we have. Is it electricity? Is it gravity? Is it magnetic? Or is it strong nuclear force? Electricity, right? Strong nuclear force is only in the nucleus, which we did last week. The gravitational force, molecules are just way too small to be affected by gravity in a microscopic way. And magnetic, they're not magnetic in the sense that some molecules are, but they're not, that they don't, the pieces don't connect. It is strictly electrical. Okay? And it's all about their electrons, which is kind of cool. Okay? It's all about their electrons. Ooh, there we go. So we need to understand how the electrons are actually organized in an atom. Okay? Electrons actually behave as if they're in these concentric shells. If you ever took chemistry before, you probably remember something about, the shell and valence electrons in these shells, right? This picture here, it's tough to read. Probably in the video it's impossible to read, but as you go out, there's all these shells that are around the atom. And by the way, this is a conceptual model. The atom does not look like this. It's all based on probabilities and things when you get down to the actual math. We're not going to worry about the math. But from the standpoint of, yeah, you say yay. Whoever said yay, right, on the test we just took, how much math was there? And some of you may be surprised at how poorly you might have done, even though there was no math. But like I said, my red pen started to run out grading that. Anyway, as you go out farther, there's a certain number of electrons that actually can be contained in these shells. And that's how we're going to describe it. And you just got to keep in the back of your mind, OK, if I learn a lot more chemistry, this is not the way it really is. But it's a good way to think about it. The first shell has 2 electrons in it, and that's all it can have. 2, it can have 1, 0, or 2, right? 2 is good, and it's full. 8, and then 18, et cetera, all the way to 32. So this is how we're going to think about it. Okay, and these are the electrons. Now, sometimes, this is also hard to see in the video, but sometimes it's easier to do this 2-dimensionally instead of 3-dimensionally. So we just have for instance, I'll just zoom in here. If you look at argon, for instance, it's got 2 electrons in the inner shell, which is full. It's got 8 in the next shell, which is full. And it's got 8 in the next shell, which also happens to be full. And do we know anything about argon? Do we know what kind of gas it is? It's a gas. It's a noble gas, right? Noble gases don't want to react with anything. And the reason they don't want to react with anything is because they've got filled up shells. Okay? In fact, all these are. Helium, neon, argon, and krypton all have all their shells filled, which is why they don't care to interact with anything. Okay? So you can get, so that's kind of, one of the reasons. And remember, elements going down in the period, in the group, are generally the same have similar chemical properties. Why? Because like their outer shell is filled in this case. Okay, if you look all the way at the other side, the ones near sodium, very reactive. Why? Because they all want to give up just one electron out of that outer shell. So we'll get to more details about that. So we got to go into a little more logistics here. We call the electrons in that outer shell, whatever level it's at, whatever the last level is, we call those valence electrons, V-A-L-E-N-C-E, valence electrons. And that means that that's just the term we use for that outer shell. Okay? And these are the ones that actually do the chemical bonding. It's those outer ones. The inner ones, don't worry about those. Whatever that outer one is, those are the ones that are bonding. Okay? And we have this, we will write this in a form that kind of shows that. So chlorine, for instance, okay? Chlorine has 2, 4, 6, 7 outer electrons, or 7 valence electrons. Well, guess what? It should have 8. Like it wants to have 8, if we can use that term, want. And because of that, it's going to be very reactive. Okay? Same. Now, carbon, on the other hand, happens to have 1, 2, 3, 4. It should also have 8 in that outer shell. Well, carbon happens to be the basic building block for you guys, right? Anything organic. And one of the reasons is it can do a lot of different, it can combine with a lot of different types of atoms because it's got all these valence, like free spots, and can combine in lots of cool different ways.
And that's why we always hear carbon-based compounds.
We are all carbon-based life forms, yes. Yep. I don't know why this keeps doing that. All right. So here's a bunch of electron dot structures. You will not have to memorize this, but keep in mind, again, look at this. Fluorine, it needs 1 more to fill that last one. Chlorine, 1 more. Bromine, 1 more. Iodine, 1 more. Whatever this one is, 1 more. Right? In the same group, you're going to have similar properties because of that outer little shell. Okay? Same thing here, beryllium, right? It's missing 1 on both. It's missing 2 basically. Okay? Same thing with magnesium and so on. Okay? That's how we end up with the properties. And that's basically why the periodic table looks like it does. Okay? All right. Now let's talk about ions. Okay? Ions are simply atoms that have either lost or gained some electrons. That's all there is to it. So an atom by itself has a certain number of electrons. And remember, the electrons are the same number of protons for that atom if it's neutral. But if it loses some, it's going to be what kind of ion, positive or negative? It loses electrons. It's going to be positive because it's got less electrons. If it gains electrons, it's going to be negative ion. Okay, so over here we have, let's see, I don't know what 11 is. Oh, it's sodium. So sodium, right, looks like this. It's got that one little extra one out there. If that one's gone, it becomes a positive ion and a sodium ion. And we do this, we say Na with a little 1 plus. Up at the top there like that. You can kind of see that right there. We designate it, we say Na with a 1 plus, like that. And that means it's a positive ion. Okay? We're going to do enough, we're going to see enough of these that you'll get used to it. So, and then of course, if we did the other way, if we said fluorine here, it's almost filled up. It's got 1 little empty electron in that valence shell, right? And if we filled it with an electron, well, now it becomes negative. So we're going to say F1 minus. And a lot of times we just don't even worry about the 1. We just say F minus. The 1 is kind of understood. Okay? How ions formed. All right. Okay, you can also form molecular ions. Right? Molecular ions are going to be generally when you gain a proton, which is basically a hydrogen nucleus, if you will. Okay, so it's kind of a little bit different. You're not talking about electrons in this case. You're saying, hey, I'm going to take this proton, which has lost its electron, and I'm going to combine it with something else. So in this case, we have water and a hydrogen ion. Well, if that hydrogen actually kind of comes up and connects to this molecule, we now call it a hydronium ion. Okay, why is that the case? We'll get into why that's the case and why H2O has this weird kind of Mickey Mouse looking pattern to it. Okay, we'll get into that in a little bit. But just you can form a molecular ion by gaining or losing hydrogen. Question?
How do they mix like the atoms and stuff?
How do they mix? You mean how does like this molecule connect to that?
Yeah, like how do they?
Well, it's electrical. right? So if you think about, so it turns out, and we'll get into this in a little bit, water, this is H2O, right, happens to be a little bit negative on this side. It just happens because of the way the structure is, right? It actually looks kind of angled like this, and you end up with a little bit of negative there, and a hydrogen plus has lost its electron, so it wants to connect to a negative. So that's how they end up combining. It's a relatively weak bond. We'll get into all those details later, but they do kind of combine there. Okay? You won't see this floating around, but you'll see it in water, for instance. You get these hydronium ions. Hydronium. Okay? All right. So have you guys heard of ionic bonds and covalent bonds? Does that remember any of that from chemistry, except for those who didn't take chemistry? Right? Okay. There's a couple different types of bonds that we're going to talk about. In other words, bonds are when atoms connect together electrically. Okay? We've got one particular kind of bond. I'll zoom in a little bit on this one, called an ionic bond. Okay? And an ionic bond is when you've got two oppositely charged ions, like that chlorine and that sodium ion, and one's negative, one's positive. Okay, when they come together and basically one gives up its electron. So sodium in this case says, good, now I can fill my shell by giving up that one electron extra that I have. And chlorine can say, aha, if I get an extra electron, now my outer shells will be filled. Okay, when they combine together, that's called an ionic bond. Okay, and we'll get into more details about that later. But ionic bonds tend to be very strong bonds. And the reason is because both atoms are very happy after they bond ionically. Notice, remember, if you lose an electron in a sodium, you got everything filled. You're pretty happy, right? If you gain one electron to fill that little spot with chlorine, you're also very happy. Now, you might ask, fine, why doesn't the sodium give up its electron and then just go on off by itself? Well, what part haven't we discussed on these? You've got the electrons. There's also the nucleus, right? And that's what's going to be positive. So if sodium lost that electron, you'd end up with a positive ion, right? And by itself, that's not going to be very, it's going to need more, it's going to need that extra electron. It's going to seek it out from somewhere because of the nucleus, right? And it can get that extra thing by having the combination between the two. It's still got the electron in the sense that it's still nearby, but really it's been transferred in some sense to the chlorine, which wants that extra electron, but now ends up somewhat negative. So you end up with those kind of ideas. You've got to worry, but you do have to think about the fact that, oh, it's still got the positive nucleus in there. Okay? I think that was a question on your test, too. Nucleus positive or negative or something. Okay? Something like that. All right. Hey, there you go. Metallic bonds. Now, we know about metals, studying them a little bit in the electricity unit, right? They are very good at conducting electricity. They are very good at conducting heat, right? And part of the reason is metals are very regular substances in that they're generally put together in these nice regular formations, especially when they're metals, or sorry, when they're solids. And the electrons, because of the way that the structure is set up, the electrons can kind of go where they want, right? They can kind of be pushed around. So for instance, this is a test question as well. If I took a negatively charged rod and I held a negatively charged rod up to this sea of electrons here, where do the electrons go? If I'm right here and this is the one I'm holding it up to, which way do they go? The electrons go. They go that way because they want to go away from the negatively charged rod. And if I touch my finger over here, those electrons have a path to go, so this becomes positive. Remember that from the test? Good. All right. So anyway, so we actually can kind of think of it like a sea of electrons. And the electrons are very movable and very easy to do. It's a weak attraction, okay? And so the electrons can move about. And that's why you get all these metallic properties, like good at conducting electricity or heat or being a good reflector or that sort of thing. Okay? So that was ionic bonds and metallic bonds. Now there's these things called covalent bonds. Now, covalent bonds are the ones where you kind of want to share electrons, not transfer them. Okay? So if you look at fluorine, remember fluorine really wants that extra electron because then it fills up its outer shell. Well, another fluorine also wants an extra electron to fill up that outer shell. Well, what if these guys kind of got together and this guy shared this one and this guy, they shared that extra electron? Can you kind of see how once they share, they both feel like they're filled up together? Yeah. So this is what happens with a covalent bond. It's not a transfer of one to the other. It's more of, hey, you've got one, I've got one. Let's make it so we each kind of have one and a half, or we each have two, but they're kind of shared. Okay? That's a covalent bond. Okay? We generally do this in our little dot diagrams with a little dashed line. Okay? When you do that. And we'll talk a little bit more about the differences between covalent and ionic bonds later. But as far as we're concerned, ionic swap the electrons, covalent share the electrons. Okay? That's all you have to think about. And by the way, well, let's, I thought I was going to the next one. The number of covalent bonds in atom can form equals the number of unpaired valence electrons. So remember how we went around the little things and there's so many unpaired ones? Like look at oxygen here. It's got 2, 4, 5, 6. How many are unpaired? 2 are unpaired. Well, guess what? Hydrogen's got an unpaired one. It can go boop right there. This other hydrogen's got an unpaired one. It can go boop right there. And now we've got nice shared electrons. Okay? And we've got some covalent bonds here because they're sharing those electrons. Okay? And now we've got water. And that's how water ends up forming. Okay? Same thing with nitrogen. It's missing 3. It's hard to see. But nitrogen is missing 3 outer electrons. And so it can combine with 3 hydrogens. And a nice covalent bond. Okay? Shares them. Right? And that happens to be ammonia. Each NH3 is ammonia. Okay. All right. You can create multiple covalent bonds with one atom. Okay. If you look at oxygen, O2. Okay. So oxygen is missing. So oxygen is missing 2, 4. So if it shares those 4, then both oxygen molecules will be nice and happy. Okay. Carbon dioxide, same thing. You're sharing 4 there. And nitrogen, same thing. N2, you're sharing. N2, you're actually sharing 3 different pairs. Okay, a very tightly bound molecule. Okay, the more bonds you share, the more stable you generally are. Okay, all right. Now we're going to get into this idea of polar bonds. Now we talked about electric, polarization on a balloon. Where a balloon, if you charge it up, will stick to a wall. I don't know if that was a test question. I forget. Maybe it was. But anyway, it sticks to a wall because those electrons will move over to one side of the balloon, and then on the wall, they'll kind of create a nice force there on the wall. Well, turns out that if you've got two atoms that are the same like this, or maybe not the same, the electron cloud kind of hovers in one place a little bit more than in another area. Okay, so yes, you've got the 2 electrons kind of shared between those hydrogens. Well, in that case, there's going to be a bigger electric force right in the middle, except versus on the ends. Okay, they're shared there, so you can kind of see with this pattern here, there's more of an electric force right in the middle there than on the ends, and it's because of the way those electrons are being shared. They have to be in the middle, so there's going to be a bigger force right in the middle. Hydrogen and fluorine, same sort of thing. You've got a nice little cloud kind of in the middle, even in fact a little closer to the fluorine in this case too. Okay, and those are polar covalent bonds. Polar meaning on one side versus the other. And you can think of that, when you think of the North Pole or South Pole, one side or the other, or the top or the bottom. In this case, one side has more of the electric field in it than the other. Okay. You can also have molecular polarity. Okay, and this is actually kind of interesting. Water, it turns out, is a polar molecule. Okay, and I mentioned this about 10, 15 minutes ago, where if you look at the structure of water, okay, because of the sharing of those covalent bonds, water ends up looking like this. The oxygen's over here, but the hydrogens are kind of near each other on one side. Okay? And what that means is there's a little more positive over on this side than on this side. And this side tends to be a little negative. Okay? So it kind of acts like, in some sense, a little magnet if you wanted to think about it that way. This side has more of a positive, this side is more of a negative. So if you took a water molecule and put it near another water molecule, right, it would line up right above it like this because the positive side would kind of connect to the negative side. Okay? Water tends to do that. It tends to bunch up. In fact, if you've ever washed your car, waxed your car, and you like spray it off, you notice all the beads of water on there? Or even if you'd like drop water on the table or something, you notice the beads of water? That's because these water molecules are combining, kind of sticking together in these little beads because they're polar and they line up like this, where they like to stick together. Water is one of those things the molecules like to stick together because of the weird shape. And the shape is based on the fact the bonds are the way they are. Okay. And so this is kind of, there you go, this is kind of the way it looks. Notice this side connects to one of the little hydrogens there. So the negative there connects to the hydrogen there. The negative here connects to the hydrogen there. Or sorry, the oxygen there. The hydrogen there connects to the oxygen there, et cetera, et cetera. Okay? All the way across. And so they tend to bunch up like this. This leads to a lot of different things. In fact, I think this is the last slide from here. This leads to a lot of different properties. Now I'm going to let some other chemistry teacher tell you the story a little bit better. And it's not Hewitt. In fact, I'm kind of disappointed. So the videos I've got, so Paul Hewitt wrote the physics part of the book. Some chemist wrote the chemistry part of the book. His lecture, I've watched some of his videos. They're terrible. They're like so like kind of patronizing, you know, which he kind of like, wow, how did that happen? You know, that kind of stuff. And not my thing. But anyway, so we will look at, let's see.
There's some definite difference in the writing structure, physics versus chemistry too.
Yeah.
The physics kind of, you can tell that Paul Hewitt wrote it.
Yeah, you can see it's, yeah, you definitely see it's different. But let me connect this up. Yeah, the chemistry's a bit dry, definitely. Okay. Let me connect this up. This guy, though, is pretty good. This guy that you'll see is pretty good. So I'll probably have to find more videos by this guy. Okay. Question?
What's this guy's name?
This guy's he's a chemistry teacher. He's going to talk about polar molecules. So want to hit the lights over there? Want to hit the lights over there?
Hi, it's Mr. Anderson. Today I'm going to be talking about water. I love this picture of a water droplet. The forces that hold this water droplet together are the same forces that allow us to survive. And the neat thing about water is that wherever we find water on our planet, we also find life. And so it's very important. And so this podcast is dedicated to water. Okay. First of all, what do we mean by a polar molecule? Well, oxygen is unique, and oxygen is unique in that it is almost the most electronegative atom on the whole periodic table. So in other words, it gets second place. The most electronegative is actually fluorine. Fluorine can even form compounds with some of the noble gases, which is pretty amazing. First of all, we should talk about what electronegative actually means. Electronegative means how much you want electrons. And so if we think about the valence electrons of oxygen, oxygen, remember, has 6 valence electrons. It would love to have 8. And so if it can just gain 2 more electrons, then it can be happy. And so if we look at this down here, so right here we've got an oxygen attached to 2 hydrogen atoms. Oxygen's highly electronegative, and so what it's going to do is it's actually going to share electrons with hydrogen, and so it's not going to form an ionic bond, but it's going to share those so unequally that it's really, really, really a polar molecule. What does that mean? It means that on one side of the molecule, so on this oxygen side, it's actually going to have a negative charge over here, and then on the other side it's going to have a positive charge up here. So we get a positive charge up here. And as a result of that, the whole molecule has a charge. And a good way to think about how that works is it's almost like a magnet. And so if a magnet looks like this, and it's got this north and this south, water's going to behave kind of the same way. And so let's talk about how that actually works. The most important bond that we need to talk about when we're talking about water is what's called a hydrogen bond. And so I have a little model for a water molecule right here. And so the red represents the oxygen and the white represents the hydrogen. And so if we were to look at this bond right here between the hydrogen and the oxygen, we call that a polar covalent bond. But these ones are special in that they have little magnets inside them. And so if I try to hold it so the two hydrogens are next to each other, you'll notice that they'll repel each other. In other words, they'll push each other apart. So it's hard for me to get them to stick together. But if I hold the oxygen next to the hydrogen like that, there will be an attraction. And so that attraction between the hydrogen on one side and the oxygen on one side is called a hydrogen bond. It's much weaker than the actual covalent bond between the hydrogen and the oxygen, but what it does is it holds that water molecule together. And so if it's water vapor and it's shooting around, there's not going to be much attraction. But when we get liquid water and the water is flowing around itself, we actually get these hydrogen bonds that hold it together and give it that property of cohesion. And so if you think about hydrogen bonds, and we'll see hydrogen bonds in like ammonia as well, sometimes with nitrogen, but usually what a hydrogen bond is an attraction between a hydrogen on one side, which has a positive charge, and an oxygen on the other side, which has a negative charge. And so in this diagram right here, this would be a hydrogen bond right here. Hydrogen bonds are really important in holding water molecules together, but they're also important in biological life. In other words, the DNA, the two helices, or the two sides of the double helix, is actually held together with the hydrogen bond. Okay, polar versus nonpolar. I have two things on this slide that are polar. So this would be water on this side. These are water molecules. And you can see that the water molecules are kind of lining up. So we get that hydrogen bond between the hydrogen on one side and the oxygen on the other. This would be a fat. And so this would be like an oil, like an olive oil, would be mostly made of this triglyceride that looks like that. So what is this made up of? Well, you can see that we got a little bit of oxygen up here, but most of it is actually carbon. And so carbon is making up most all of this fat. Now carbon is not highly electronegative, kind of fits somewhere in between the two. And so this whole molecule, this fat molecule, is a nonpolar molecule. And you've probably noticed other things that are nonpolar, like oil or gasoline. If you pour them into water, they don't mix. And the reason why is that water has a charge, and so it's only able to grab onto parts that are also charged. And so you might be a little confused with polar and nonpolar, but a way that I always remember this is that like dissolves like. And so if you want to break down something that's charged, then you should use a charged particle. If I want to break something down like fat, what am I going to do? I'm going to have use something that's nonpolar to break that down. So I've come up with 5 properties of water that are important just based on it being a polar molecule. First one is called the high specific heat. High specific heat is a measure of how much energy you have to put into a molecule to actually change its temperature. And so remember, temperature is the speed of those molecules as they move around each other. And it's way easier to heat up something like alcohol. And the reason why is that alcohol doesn't have much of these hydrogen bonds, and so it's not held together, so it's easier to heat it up. A real world example, I'm actually in West Yellowstone right now at a ski. My kids are at a ski camp, but we're just skiing down here. And this is the temperature in West Yellowstone. This is the temperature last night was negative 22 degrees. And so that's pretty darn cold. Now, if we were to go straight across as far as latitude, we'd end up in Seattle. And Seattle weather right now is going to be much nicer than it is in Yellowstone. And the reason why is that Seattle's sitting right on the ocean. And as that ocean absorbs energy during the summer, it doesn't change much because water has a high specific heat. And likewise, during the winter, when it cools down, it actually is giving off some of that energy. And so it keeps Seattle fairly temperate. And so high specific heat of water, it explains why it takes a long time for water to actually boil when you put it on the stove. Okay, next thing that's important as far as these properties go is that since it's a polar molecule, it's a really good solvent. And a solvent, remember, is something that breaks down a solute. And so I love this diagram right here. What we have is sodium chloride, which is just regular table salt. And that's an ionic compound. Remember, we have these cation sodium ions and these anion chlorine ions. And so what happens with water, if we look right here in the middle, is that chlorine is actually surrounded, since it's a negative charge, it's surrounded by the positive hydrogen atoms. And so they'll circle around that ion, and likewise the sodium, which has a positive charge, is surrounded by the negative oxygen atoms. And so water works as a really, really good solvent. And in fact, that's why we're filled up mostly with water. It keeps our heat the same, but also it moves nutrients in around. It's really good at that. Next, we have cohesive properties, okay? So water, remember, is held together by this hydrogen bond. And so if we have a group of these molecules, they'll all be held together. And so we get these cohesive forces holding the water together. And so in this picture, right here, we've got a paperclip that's actually floating on water. So water has a high surface tension. And the reason why is if we were to look way down here, there's these cohesive forces between the water molecules. And it almost works like a skin, giving surface tension to that surface of the water. Next one would be capillary action. Capillary action works like this. If you have one water molecule attached to another water molecule, you can get this long string of water molecules like this. And so how does water get to the top of the tree? The way it works is you'll evaporate one water molecule at the top, and as we lose that, the water will flow up, and so we have this long flow of water molecules moving all the way up the tree. So that's capillary action. An example of that, let me try to sketch one out, is if we had a tube, let's say we had a tube that looked like this, and then that tube was just sitting in water. Water's going to start flowing up the tube, and the reason it flows up the tube is the water molecules are attached to water molecules farther down. If I were to make a thinner tube, so let me try to make a thinner tube. Let me try. A thinner tube, the water would actually flow up a larger amount. Or if I were to make a microscopic tube, the water might flow all the way up and even start to flow out the top. And that's called capillary action. And so the microscopic tubules or tubes inside a tree are actually called xylem. And then the last thing is the idea that as water becomes colder, it actually becomes less dense. And so the density of water is 1.0, so that's going to be grams per cubic centimeter. But the density of ice is actually closer to 0.9 grams per cubic centimeter. And that's unlike anything else you can think of. If you've ever played basketball on a cold day, you realize that the gas inside the basketball is actually compressing, and so it's becoming less dense. But water is unlike that. And so the reason why, again, is these hydrogen bonds between the water molecules. And so what it does is it creates these beautiful hexagonal shapes, and you'll get these beautiful lattices. And that's why on this picture right here, we've got snowflakes, and those snowflakes are held together by these beautiful, based on hexagon kind of patterns. And the reason why that we see that is, again, those hydrogen bonds. And so water is actually going to have a greater density than ice, because as those water molecules actually start to slow down, they will form these beautiful kind of three-dimensional structures. And so that's it as far as water goes. On the next few podcasts, I'll talk a little bit more about solutions and how they actually break down material. But for now, that's a good introduction to water.
There you go. All right.
So,
Question, yeah.
speaking of snowflakes,
Yeah, snowflakes.
now, lots of times snowflakes are so small you can't actually tell you can't see the structure. You have to look at a real microscope outside of the building.
Yeah,
But sometimes you can actually identify what they look like.
sure.
Now, is that
You can identify
because-
snowflakes, yes.
Is that because the snowflakes are larger? Is that
Sure.
because the weather is colder, or is there more?
I'm not sure the weather, the coldness determines the size of the snowflake. I'm not sure. I mean, basically what he was saying is the
density
snowflake.
of the clouds before they come down?
I'm not sure. I'm not sure what caused the size of the snowflakes. I'm not sure. That's something you might want to Google.
Okay.
I would say, yeah. Okay, so you want to hit the lights? All right. believe it or not, I'm going to let you go. So we're going to go out a little early tonight. Good job on the test. I'll have it graded. I can grade as many. I'll finish grading right now. So if you guys want to stick around for your grades, I can do that. And otherwise, I will see you tomorrow for lab. If you could bring your computers again, that'd be great. And otherwise, I'll see you then.